Welcome to this virtual session of the International Conference on Acoustic, Speech, and Signal Processing, or ICASSP 2020. Special thanks to our partners across the signal processing community for helping make this virtual event possible.
Good afternoon, everyone. Yosua Bengio is recognized as one of the world's AI gurus and a pioneer of deep learning. This recognition is best shown by the 2018 Turing Award that he received together with Jeff Hinton and Yann LeCun. The award is considered as the Nobel Prize for Computing, and the trio has been named as godfathers of AI. Yosua has been a professor at the University of Montreal since 1993. In addition to holding the Canada Research Chair in Statistical Learning Algorithms, he's also the founder and scientific director of MILA, the Quebec Institute of Artificial Intelligence, which is the world's largest university-based research group in deep learning. In 2018, he collected the largest number of new citations in the world for a computer scientist. The list of other awards is just too long for this brief intro. When I invited him to be one of our keynote speakers, he replied on the same day, saying that ICASSP had been one of his early publication venues when he was still a PhD student. In fact, his Google Scholar page shows his very first conference paper at ICASSP 1988 and others in this conference in 89 and 90. We are all very, very happy and honored to have Yosua return to his first international conference. I was looking forward so much to introducing him in person. Unfortunately, we have to do this remotely, but with the possibility of having a much wider audience. So here's Yosua Bengio to talk to us about deep representation learning.
Hello, my name is Yosua Bengio, and this is a keynote presentation for ICASSP 2020. This talk is on deep representation learning. And I'm going to talk about how deep learning could be expanded towards modeling of higher level representations and beyond the limitations that we currently face. So deep learning was an idea centered on representations and learning representations, and more specifically about learning multiple levels of representation, hence the name deep learning, with the idea that higher levels of representation correspond to more abstract aspects of the world. And so the challenge is to discover and disentangle those factors of variation, because modeling the world at that level would lead to much easier generalization and transfer. We've made huge progresses with deep learning, but we're still far from human-level AI. For example, most of our work is based on supervised learning, which requires humans to specify these high-level abstractions in the form of labels. And the systems we have make all kinds of mistakes that humans don't. For example, these adversarial examples, like in the picture of the dog, which is correctly classified, but then if we change the pixels a little bit, we can get the system to say it's an ostrich. Also, when industrial systems are trained on some data, even large data sets, but that deployed in other contexts later in time, they might fail because the distribution has changed. So there are many steps required to make significant progress towards human-level AI, which go beyond just acquiring larger data sets and doing more engineering to have larger models. In particular, we want to be able to adapt to these changes in distribution, to new tasks much faster in a way that would be comparable to how humans are able to do it. And that's important in practice because if you're a robot, for example, there's a limited amount of experience that you can have, and your experience is limited because some actions could be lethal or dangerous. And for really complex aspects of the world, including interacting with humans, we don't have good simulators. So the techniques that currently work in reinforcement learning based on simulators, for example, for games, are not easy to apply in the real world. Also, we want the machine to be able to more independently discover these higher level concepts, even though we can probably help the machine by interacting with it in natural language. We'd like our machines to understand better than they currently do the world around us and go beyond the currently fairly shallow and superficial understanding that they have. So the dream of discovering and disentangling high-level explanatory variables is far from achieved. For this, we need to build machines that do a better job of understanding how the world around us ticks. Otherwise, they can cheat by relying on superficial statistical regularities, and they remain vulnerable to out-of-distribution examples. So how do humans manage to do such a good job at these changes in distribution? Well, we believe that they're able to do it because they have a more accurate model of how the world works, and in particular about the underlying causal relationships. That allows us to predict future situations, even though they are very far from anything that we have experienced ourselves. For example, I've never died in a car accident, but I can imagine what would happen in different circumstances that could lead to me dying in a car accident. So this is an essential component of reasoning, of intelligence, and of science. So we need to build machines that can generalize beyond their training distribution. And usually those changes in distribution are due to a causal intervention, which is going to be a big part of what I want to talk about. So the objectives we want to set ourselves are deep learning algorithms that can discover causal representations, figure out what are the causal variables that explain the data, and figure out the causal dependencies between them. In other words, build a causal graph, like in the figure, where each node represents a high-level variable, and the directed edges capture the causal structure so that one node is a direct cause of another node. Now, to discover these high-level variables, I believe that we need to put priors on what to expect from them. Otherwise, there might be many ways to explain the data, which in terms of the log likelihood, for example, might not tell us what are the right higher level representations. For many years, people have been studying the question of disentangling latent explanatory factors with the very strong assumption of marginal independence. In other words, these high level variables are independent of each other. I believe this is too strong, and the reason for believing this is if you think about the kinds of high-level variables which we manipulate with language, which I shall call semantic variables, they are clearly not independent. So if I take my phone and I drop it, there's a very strong dependency here between the actions, the objects, and the consequences in terms of these high-level variables, which we can state in a sentence like, if I drop my phone, it will fall on the ground. So those kinds of fairly sparse but strong dependencies is something I've been talking about for a few years under the idea and research program of the consciousness prior. In addition to understanding the dependency structure of these variables, we want to understand how they can change over time because things happen in the world because of interventions and causal dependencies. Many of the words we manipulate in language, and so many of the concepts we would like to represent at this high level, have to do with causal variables like objects, agents, and actions and intentions. In addition, another clue we could use in our machine learning work is that the high-level variables have a simple relationship to words and phrases in natural language. So we could jointly learn to represent low-level data like video and to converse at the high level with humans about the content of these images. Now, a lot of the work in representation learning has been focused on methods that evaluate the quality of the learned representation in terms of what happens at the low level, for example, in pixel space, like a log likelihood in pixel space or some proxy for it. However, it doesn't look like this is the way humans model how things change with time. We seem to capture this more at an abstract level. Now, if we were to learn an encoder that maps the low level to the high level and then learn how the high level changes, there are challenges. So if we look, for example, at the log likelihood at the higher level between the different time steps of these high level variables, this might be a good thing to do, but if we optimize the encoder that maps low level to high level using this objective, then we could converge to a trivial encoder that maps the inputs to trivial, like constant, very easy to model representations. Now, the good news is there's been some progress using notions of information theory and neural nets that can estimate mutual information to help us address some of these problems, in particular the work of Belghazi et al. And Helm et al. In the last couple of years. Another issue with our current approaches is how our theories in machine learning deal with changes in distribution. Our current theories are basically about what happens when we get all of our data from the same distribution. But in the real world, there are these changes that I've been talking about. And we need theories that tell us about what happens when we have these changes in distribution, what kind of generalization are we going to get, and how can we get better generalization. So this raises an interesting question. How to adapt to those changes in distribution, how to learn in a way that makes us learn faster to these changes, and I'll talk about meta-learning as an important potential tool for this purpose. Another aspect that we'll talk about is how we represent knowledge. So when there's a change, because maybe we encounter a new situation or a new task, we would like, and humans do, reuse the pieces of knowledge that we already have in order to find a quick solution to the new problems. So this requires modularizing knowledge in the appropriate way so that we can reuse the different bits and pieces that we have learned fairly easily without having to relearn a lot of stuff when there's a change in distribution. Now, let's consider a little bit the meta-learning aspect. So what is meta-learning? It's basically about having two levels of optimization. In the inner loop, we have the usual learning. In the outer loop, we have meta-learning. So an example of this, which I've been working on in the early 90s, and Schmidhuber as well has been thinking about around those years, is the relationship between evolution and individual learning. So evolution is an optimization process in some sense. And for each individual, there's an inner loop of optimization in the lifetime of the individual. In the work I did with my brother on this in the early 90s, what we innovated with is the idea that we can take the loss that is being computed in the inner loop at the end of the adaptation and backprop through it in order to optimize at the outer level. So this is what we currently call meta-learning in many cases. And actually, it corresponds to a general problem in optimization called bi-level optimization. Now, what's interesting is that in recent years, we've moved from the notion that this applied to describe the outer loop is evolution, inner loop is individual learning, to the situation what happens within the lifetime of an individual, where within my lifetime, there will be different changes in environments, changes in distribution, and would like to have fast adaptation like in transfer learning. So this is a lot of where current meta-learning is. You can also generalize this, once you think about it this way, to consider multiple timescales of learning. So you have aspects of the world that are very, very stable and that you want to learn across very long timescales. You have aspects of the world that change very quickly and you want to have very fast adaptation for them. But you want to learn the outer levels, taking into account the process by which the inner levels are being computed. The nice thing with ideas of meta-learning is that it gives us a handle on a form of end-to-end learning to learn to generalize or to do transfer learning quickly. Now, there is another ingredient that I talked about besides the meta-learning aspect is how we're going to structure our models, how we're going to decompose knowledge into pieces that can be recombined easily. So that's a notion of compositionality. Compositionality is already something that is helping deep learning be very successful. So the very old and basic notion of distributed representations, which was introduced by Jeff Hinton in the 80s, has been shown in the last few years to give a theoretical advantage because of its compositional nature. And similarly, the composition of layers on top of each other also gives an exponential advantage, again, based on theoretical arguments. But we see that deep learning is working, and it's probably in big part because of these compositional assumptions that are built in the algorithm. But there's more compositionality that our current deep learning does not exploit. And this is something connected to the form of compositionality we find in language, also called systematic generalization. This is something we use in abstract reasoning and analogies, and this is a lot about what I want to talk today. So there's a lot of work trying to understand this notion of compositionality, especially in language, and how humans are able to combine different pieces of knowledge to understand a new piece, like in the image, the different vehicles that we already know allow us to understand the function and how to operate this new vehicle that does not actually exist. So this notion of dynamically recombining existing concepts is a new form of compositionality that we need to incorporate in deep learning. And of course, it's very powerful in language. We use it all the time, and it's been studied in linguistics. What is interesting is that it allows us to explain new observations or to imagine new situations that we have never seen before and have zero probability under the training distribution. It's not just that we have never seen them in the training data, that even if we saw an infinite amount of data, we would think that this is a zero probability event. For example, I can tell you a science fiction story and you can understand it. You can go to a country where you've never been, where people drive in the wrong side of the road, and you can reason about it and quickly learn to deal with that. Now, what's interesting is that people are starting to study this ability of systematic generalization, and a lot of existing neural net architectures don't seem very good at it. What's interesting is different architectures seem to react differently to this problem. So although on the training distribution and on a test set of the same training distribution, we might not see a difference between different architectures, when we confront these different approaches to a changed distribution, which essentially is the same concepts that the learner has seen, but combined in new ways that were not likely under the training distribution, we see that different architectures react differently. And that's interesting. Now, this question of recombining high-level concepts is at the heart of high-level reasoning. And there's a really nice distinction between low-level and high-level aspects of the world, which is embodied in the discussion around System 1 cognitive abilities versus System 2 cognitive abilities that psychologist and Nobel Prize winner Daniel Kahneman has talked about, for example, in his book, Thinking Fast and Slow. So we have two systems that he talks about. And this is my characterization of these systems. To first order, we can think of the difference between the two systems along different axes. But one of them is the system 1 computation in your brain is happening in an unconscious way, whereas system 2 is happening in a conscious way. So in system 1, we have everything that is intuitive. These computations can be done fast in one step in parallel. And they're non-linguistic. It's hard to explain how you come to these conclusions. It captures implicit knowledge, right, that can't be explained. And this is also where current deep learning is very good at. On the other hand, system 2 is slow. It involves a sequence of steps. This is how we can reason with logic. This is how we plan. And because it's happening at a conscious level, we can explain what is going on. This is also the kind of skills we use when we design algorithms or we program. It's about aspects of the world that we can render explicit, that we can talk about. And this is where I would like to see deep learning expand towards what you might call deep learning 2.0. Now, one of the interesting elements of the manipulation of high-level concepts that our brain does is that it involves these conscious thoughts and it involves attention. These conscious thoughts refer to very few aspects of the world at a time. And the way to see this is you can explain your thought. You can say a sentence that summarizes your thought. It has very few words. And we use attention mechanisms in our brain in order to select those aspects that go into a thought. The mechanisms for the selection is unconscious. We don't see ourselves deciding what goes into a thought. It just pops into our mind. But that selection creates a very special property of how our understanding of the dependencies between those concepts is structured. And I'll come back to that. So we use attention mechanisms to focus on a few things at a time. The good news is there's been amazing progress in deep learning in the last few years, thanks to these soft attention mechanisms. We introduced a form of these attention mechanisms for machine translation at the ICLR 2015, and it has been a huge success for machine translation, but pretty much for all of natural language processing, which where state-of-the-art methods now mostly use attention mechanisms, for example, as you find them in transformers. Now, what these attention mechanisms allow you to do is to focus on pieces of your overall knowledge, or one or a few at a time. And this is related to the other question I've been talking about, how we decompose knowledge into pieces. We want these pieces to be reusable. We want those pieces to be stable for the most part. And we want to be able to deal with the changes that happen to how we view the world due to interventions by agents that change something in the world. So the assumption I'm going to talk about is that those changes are localized, meaning that most of the knowledge we have about the world doesn't need to change when something happens, somebody does something, there's an intervention. And we can focus on just a few aspects, a few variables that need to be adapted in some sense. So the first work I want to spend a bit more time on, that's more recent, that digs into this question of decomposing our knowledge into pieces is the work on independent mechanisms and recurrent independent mechanisms. So these rims are a particular kind of recurrent nets that can be used anywhere you would use a recurrent net. But instead of having a full connection matrix between all the units from t to t+1, there is a very strong structure in how the information propagates from t to t+1 around modules. Within each module, it's like a regular recurrent net, and you have full connectivity. But between modules, attention mechanisms are used to decide which information is sent from what module to what module. And the attention mechanisms are also used to create a sort of top-down attention where different modules compete in order to attend the input. And this is something we see in conscious processing in the brain as well, where depending on the input and the context, only some modules that are relevant seem to be activated and are going to take center stage in your consciousness, whereas the others remain in the unconscious background. So this is a bigger picture of the RIM architecture. We have these multiple recurrent and sparsely interacting modules. Each has their own dynamics, and they communicate through key value pairs, just like in transformers. This is used in order to create a bottleneck of communication, inspired by the bottleneck of communication that we observe with conscious processing in theories like the global workspace theory. The way that this is achieved relies on the same kind of mechanics that you find in transformers. So they take as input and produce as output not standard vectors, but sets of objects. And each object can think of and is represented with a key value pair. So the keys are used to decide on how much attention is going to be given to a particular object, whereas the values drive the content that is being sent from one module to another module. In other ways, the mechanics is very similar to what you find in transformers. We've run a number of experiments on different tasks with these recurrent independent mechanisms, and we focused on how they seem to perform better out of distribution than other recurrent nets, and including transformers. So that's interesting because this notion of modularization that I've been talking about seems to be providing advantages in terms of out of distribution generalization. We've also tried them on reinforcement learning tasks as a drop-in replacement for LSTMs in a PPO setting for Atari. And what you see in the figure for each bar corresponding to one of the Atari game is the normalized improvement using RIMs versus LSTMs on the LSTM PPO baseline. And so there are many games for which we get an improvement and a few games where we lose, but overall there's a significant advantage. Okay, so now let's switch back to the question of how things change in time in terms of how distributions change and how causality comes in. So there is this really important hypothesis that is very well described in the book by Peters, Jensic, and Shopkov. It's the hypothesis that there is a way to describe the world and modularize knowledge into these modules, which now they call mechanisms, because you're thinking about causal structure. So how information, not just information flows, but also how this represents causal effects. So each of these mechanisms captures a piece of the puzzle of causal effects. And the hypothesis is that when there's a change in distribution, it is typically going to involve a few of these mechanisms. And these mechanisms have their own parameters, but these parameters are independent of each other. So we call these mechanisms independent mechanisms, hence the name in the RIMs. So the assumption is that changing one mechanism does not require changing the others. What it means is when we have a change in mechanism due to an intervention, if we have the right modularization of knowledge, then it will involve only changing a few of these mechanisms. So now the question is, how can we discover these independent mechanisms? How can we factor knowledge in the right modular way? Now let's see how we can go wrong first. And for this, we studied a very, very simple scenario. We have two random variables, A and B, and we can represent the joint distribution of P of A and B in various ways, but in particular, in terms of conditional distributions and a directed graphical model, we can represent it as either P of A times P of B given A, or P of B times P of A given B. And what's interesting is, although the two factorizations are equivalent in terms of the likelihood in the training data, we can think about what happens if there is a change in distribution due to an intervention. If somebody changes A, in other words, changes the marginal distribution of A. If you have the wrong factorization, P of B times P of A given B, the change in P of A is going to have to be reflected in both modules, the parameterization of P of B and the parameterization of P of A given B. So I think this is a profound observation, because what it tells us is that if you don't have the correct factorization of knowledge, you end up with your whole system trying to adapt. And I think this is something involved in our current difficulties with changes in distribution, with continual learning, domain adaptation, poor transfer, catastrophic forgetting. In a neural net that we typically have these days, when there's a change in distribution, it's like if every weight and every neuron wants to participate in fixing the problem. Me, I want to fix the problem. Okay, and from the point of view of gradient descent, this may look like the right thing to do. But from the point of view of robustness to these changes and how many examples are going to be needed to adapt to those changes, this may be a bad thing. So how can we fix this? So the idea we've explored in this paper, which just appeared at ICASSP 2020, called a meta-transfer objective for learning to disentangle causal mechanisms, is that we're going to take this property of good factorization of knowledge that they lead to fast learning. We're going to turn that into a useful signal. So whereas in the past, people have been looking at changes in distribution as a problem, as a hindrance, we can take the loss, that is the errors we make when there's a change in the world, because we have to adapt and we're not doing well initially. We can use that as actually a source of information to optimize our choices of how to structure knowledge. So I want to quote Leon Boutou, who gave an invited keynote last year and said, nature does not shuffle environments. We shouldn't. In other words, the common practice in machine learning of taking your data and shuffling it so that all the examples come from the same distribution is very convenient if you are only considering the IID scenario where the test data is also going to come from the same distribution. But it's not realistic. In the real world, things change. There are changes in distribution. And so we need to not throw away that information and use those changes as a signal to find out what architectures, what parameterization give rise to better robustness to those changes. So to dig a little bit deeper in this, we have to go and think more about what causes these changes in distribution. So remember, what I've been saying is those changes are due to an intervention by an agent, typically. And the reason it makes sense to think that those interventions are localized in the overall scheme of all the things we know is because these interventions in the physical world that we know typically have to be localized in both space and time. When I do something, it can have an immediate influence in my neighborhood, but only in a few things, like I'm picking up my phone. it's hard for me to do a single action that will immediately cause a lot of things to change. Of course, downstream of the causal chain, it could change a lot of things, right? But that's precisely why we need to capture that kind of causal structure. Because if we can pinpoint those changes to a few variables, it's going to be much easier to make sense of those changes. Think about how humans manage to understand those changes. They typically communicate with language to provide an explanation. So if there is a single sentence that explains the change, and pretty much all of the changes that we are able to deal with can be summarized in natural language in one or a few sentences. And it means that that change is localized. And so that assumption is not an assumption about the distribution. It's an assumption about how the distribution could change. Okay? So it's an assumption that the distribution, the joint distribution of the high-level variables tends to change in a localized way. So the example I sometimes give is if I put on my dark glasses, there's only one bit about the world that has changed, is that I have put my dark glasses. And yet, at the pixel level, what I see is incredibly different. Everything is dark, every pixel is darker. So if I were to try to explain the world at this low level of pixels, it would be very difficult. I need to invoke this latent high-level variable, which is this one bit about dark glasses, sunglasses, in order to come up with a simple explanation that I can communicate with language. And it's not just good because we can communicate with language, it's good because it allows me to adapt to the change quickly. And that means to have good out-of-distribution performance, which is what we want. So this is interesting because if I have the right model, if I have the right representation of the high-level variables, then I'll need few observations in order to adapt to those changes. So we get, as a consequence of having the right representation and the right higher-level joint distribution structure, the causal graph, we get good generalization in terms of changes in distribution, small out-of-distribution sample complexity, how many examples I need to adapt, fast transfer, all of these are equivalent. Okay, so what can we do with that? Well, we can turn this speed of adaptation into an objective function. We can obtain the information about what is a good representation and what is a good causal structure by optimizing the speed of adaptation. So we use the out-of-distribution generalization as a training objective. So now we're in a meta-learning framework, right? We're saying we're going to look at the inner loop, how well it does during a change in distribution, and we're going to backprop or whatever, do credit assignment to find out in the outer loop, which is my stable knowledge about the causal structure, for example, and which are the high-level variables, what are the good choices there, such that in the inner loop, things go well. So that gives us a training signal for factorizing knowledge. The speed of adaptation, the out-of-distribution performance, gives us a training signal for discovering good representations and how the high-level variables are related to each other. Okay, so this is what we've done in two papers. So the first one I already mentioned. It studied first the case of just two variables A and B, where we discover whether A is the cause or B is the cause. And then an extension of it where we don't observe A and B directly, we observe a transformation of A and B, like a rotation in X and Y. So we only observe X and Y, and we try to infer variables A and B such that there is a causal structure. You have to realize that in the pixel space, there is no causal structure. Like, in other words, there's no simple causal structure. That there's no pixel that causes another pixel. But in the abstract space, there is very strong causal structure, right? So by optimizing the speed of adaptation, we discover high-level variables, and we discover how they're causally related to each other. What we see in the figure is what happens is this meta-learning procedure is what this meta-learning procedure is exploiting. So in one transfer learning episode, where on the x-axis here we see the number of examples during the transfer, we see how two different possible causal models, A causes B or B causes A, are performing. And the correct causal model, A causes B, has its likelihood go up much faster. Right? So there's a lot of signal here to distinguish between the two possible causal explanations, just in the speed of adaptation. What's interesting also is that if you had a lot of data and you look at the asymptotic performance, then the two models are indistinguishable, and this is the well-known result. That's why just pure observational data is not, telling us much about the causal structure, or at least it leaves a lot of ambiguity. Very early on, when you see just 0 examples, you don't have a lot of information either. But it's in the very early moments where you see just a few examples, like a handful of examples, 20 examples, that's where you have the strongest signal to separate one causal hypothesis from the other. So we also have ongoing work on the theoretical aspects of this, and a more recent paper where we generalize this to a larger graph. So, okay, it's nice to do this nice toy experiment with 2 variables, but how about like a larger graph? So in the paper K et al. 2019, we consider the problem of generalization to a larger graph, which is not trivial because whereas previously we could just enumerate all the possible causal structures, if you only have 2, that's easy. If you have a larger graph, you've got an exponential explosion of the number of possible graphs. So we introduce a parameterization of the belief about what is the correct graph as a distribution that is factorized with respect to all of the edges. So for each edge, we learn a probability for each directed edge, probability that it's present or not. And we find that if the learner also tries to do inference over the intervention, in other words, which node was modified. Like in the previous work that I just mentioned with 2 variables, the learner doesn't need to know where the intervention is happening, which variable is being modified. And in general, for a learner, it's hard to know that, except if the learner is the one doing the action, which of course happens. And so when you have clues about what the intervention is, or you do inference over it, you can actually learn the causal structure much faster, which makes sense. Right? If you think about babies, initially they don't move much and their causal inference might be slow and weak. And as soon as they start being able to poke around, they can learn much faster. So let's try to conclude about the many things that I've talked about in this presentation. So I've talked about limitations of current deep learning in terms of out-of-distribution generalization, in terms of being able to discover high-level representations. And what I've drawn is a research direction to try to address those problems, to bring deep learning from its current strength in system 1, capturing the intuitive dense dependencies that we see at the perceptual level, to a system 2 extension of deep learning, which would use attention mechanisms and a modular decomposition of knowledge and being able to capture causal dependencies in order to be able to give us the tools for achieving the kind of system 2 abilities that humans are good at, as well as system 1 abilities. And one of the most important part of my message is in order to achieve these things, and especially the changes in distribution aspect, we need to make assumptions about the high-level semantic variables. And so it's interesting to write down those assumptions, as each of them can bias better generalization. And if these assumptions are fairly simple to express, you could imagine that evolution could have discovered them. So the core assumption, which I started with and is described in my paper on the consciousness flyer, is the idea that the high-level variables have a joint distribution that has a sparse structure. So if you represent a joint as a factor graph, the number of edges of that graph is small. In particular, the number of edges per factor is small. And that can be verified intuitively by looking at the kind of dependencies we're able to express with natural language. Okay, but that's this one aspect. Another one I talked about is that these high-level variables refer to causal aspects of the world. They refer to agents, which are causing things. They refer to actions and intentions, which mediate how an agent has an effect. And they refer to controllable objects, which are typically effects of those actions. I've also mentioned how these high-level variables have a simple relationship with natural language. This is something we ought to be exploiting. In fact, we're already exploiting it when we use human-provided labels, but we can go beyond single words. And that would be the basis of things like grounded language learning, where we jointly learn about the encoder that maps low-level data to high-level representations, as well as the transformation between those high-level representations and sentences, for example. One hypothesis I didn't have time to talk about is that this sparse joint distribution has even more structure. It has a kind of parameter sharing structure where you don't have independent parameters for each factor. If you think about each factor as a rule, the same rule could be applied on many variables, right? So when I say, if I drop my phone now, it will fall on the ground, this rule also works for other phones and other moments, right? So this parameter sharing structure introduces the notion of variables and arguments, which of course we use in programming and logic. And this is also something that can be incorporated in deep learning and that we need to incorporate in deep learning. The other really important assumption that I talked a lot about is how things might change in the world. So this is essential. Like if we don't make any assumption about how distributions can change, then they could change in arbitrary ways, and then we have no way to say anything about generalization to these modified distributions. So it's super important to think about the plausible ways in which distributions can change. And so in this talk, I've talked about localized changes that are assumed to be due to causal interventions in this high-level semantic space. And I've talked how we can take advantage of this assumption in order to learn about what the variables should be in the first place and what is the causal structure between them. One related assumption is that the part of the model that maps the low level to the high level should be something stable. In other words, when there's a change in distribution, I don't need to adapt my encoder. I just need to do a little tweak at the high level, right? So our memory system is mostly about the high level variables. Like the events, remember, in our memory are not about pixels. They are about abstract variables we can name with language. And so there's a lot about the world which is actually stationary. If we had the right encoder, we could keep it for our lifetime. Of course, we are learning the encoder as we go, but it's more of like a normal learning problem where as we go, we adapt our learner. Whereas at the high level, we have these fast changes that allow us to keep with new tasks and things like that. And finally, another assumption I didn't have to talk about has to do with reasoning and credit assignment. So we use our high-level reasoning to imagine the future, but also understand the past so as that we can be doing credit assignment. And because of that sparsity structure of the dependency, typically we only need to look at short causal chains. And the reason I believe this is a good hypothesis is because we can explain with words, again, a chain of dependencies. I mean, of course, there are things in the world that don't satisfy this hypothesis, and usually they are the things that humans are bad at explaining with words. But remember, the high level is capturing the aspects of the world which can be explained through language. And then the other aspects which exist and are important will be captured by the system one part. So thank you very much. Thank you for having listened to my presentation. And if you have any questions, I hope you can ask them on the chat.